We often imagine dinosaurs as armored fortresses or fearsome, toothy giants. But at the heart of our understanding lies something deceptively simple: bone. For generations, paleontologists have treated the skeleton as the ultimate blueprint, the central truth of every organism we study. Yet, as we know, bones are only part of the story. For one small, seemingly ordinary early ornithischian, the Psittacosaurus, the real mystery lies not in its sturdy skeleton, but in fragile, soft tissues that by all rights should have vanished millions of years ago. Along its tail, scientists have discovered a strange and unexpected display: long, fibrous, quill-like bristles rising from the vertebrae. These delicate structures defy the rules of fossilization, pushing the limits of what we thought the fossil record could ever preserve. The very name Psittacosaurus, meaning parrot lizard, reflects its distinctive beak, perfectly adapted for cropping tough vegetation. It is one of the most abundant dinosaurs known to science, with hundreds of specimens unearthed across Asia. From its skull and posture to its patterns of growth, we can reconstruct its life with remarkable confidence. By all accounts, Psittacosaurus should be one of the least mysterious dinosaurs of the early Cretaceous. But here is the paradox. Among those hundreds of skeletons, fewer than 1% preserve any trace of skin, scales, or soft tissue. The animal most familiar in bone becomes an enigma the moment we look beyond the skeleton. This is a lesson in taphonomy, the science of how organisms decay and become fossilized. The fossil record is not a complete book, but a heavily edited manuscript, one biased toward hard structures that resist time. Soft tissues, skin, quills, feathers, are almost always erased long before fossilization can begin. And yet, every so often, conditions align to create what can only be described as a geological miracle. In rare sites, the chemistry of the earth, the absence of oxygen, and the speed of burial converge to preserve what should have decayed. For Psittacosaurus, it is in these extraordinary moments that the impossible survives. Delicate impressions of scales, and most astonishingly, 6 stiff, bristle-like quills jutting from the tail. These are not plates of armor. They are not feathers in the avian sense. Instead, they appear to be keratinous or collagen-based shafts anchored into the flesh and fascia of the tail itself. Their existence raises profound questions. Why did they evolve? And how did they survive in just a handful of specimens when hundreds of others left behind only bare bone? The answer lies not in the biology of the dinosaur, but in the unique circumstances of its death and burial. We call this taphonomic bias, the selective filter that allows some features to survive in stone while erasing countless others forever. These rare individuals, those preserved in exquisite detail, become keys to unlock the hidden truth of an entire population. They remind us that the fossil record is both a gift and a limitation, a window into prehistory that shows us much, but always leaves part of the story untold. And so, the Psittacosaurus, once dismissed as an ordinary parrot lizard of the early Cretaceous, emerges instead as one of the most enigmatic survivors in paleontology. A creature whose mystery lies not in its abundance, but in the rare, fragile traces that time, by sheer accident, allowed us to see. The key to understanding the Psittacosaurus quills, and indeed any preserved soft tissue, is moving beyond general probability to forensic paleoecology. The exceptional quality of these specimens points toward a phenomenon known as Lagerstätte preservation, a rare geological event characterized by fine sediment deposition in an oxygen-deprived or anoxic environment. This is the crucial intersection of biology and geology that allows the anomaly to exist. In an anoxic seabed or lakebed, the decay-causing bacteria cannot thrive. This halts the rapid breakdown of organic matter, providing a narrow window where the delicate integument, the quills and scales, can be gradually impregnated and replaced by minerals, thus being fossilized in exquisite detail. When we analyze the high-resolution fossil images, the 2D vector diagram illustrates the astonishing process of mineral replication. We see not just the impression of the scales across the body, but the actual preserved structure of the quills emanating from the dorsal surface of the caudal vertebrae. These quills are rigid, distinct, and appear to be arranged in multiple parallel rows running down the tail. This anatomical complexity is the reason the specimens are so valuable. They transform the Psittacosaurus from a standard skeletal case study into a specialized problem in comparative biomechanics. Our initial analysis must rigorously address the structure. The quills are likely composed primarily of keratin, similar to hair, feathers, or fingernails in modern organisms. They are stiff, but would have been relatively brittle, which leads us directly to the mechanical analysis. Could these quills have been defensive? This is the immediate, intuitive assumption often presented in popular narratives. However, when we apply the constraints of physics and comparative anatomy, this hypothesis quickly enters the realm of outlier, disputed study. If we perform a theoretical finite element analysis, FEA, simulating the impact of a medium-sized predator, say an early Cretaceous Sauronidolestes, we see that the tail quills are structurally inadequate. They lack the robust attachment points and the underlying muscle fascia required to withstand puncture or shearing forces. Furthermore, they are located on the tail, an organ primarily required for balance and locomotion, sacrificing its kinetic efficiency for minor, localized defense seems an evolutionary trade-off the Psittacosaurus lineage would likely avoid. Therefore, we must dismiss the hypothesis of physical defense and pivot our inquiry to other functional mechanics. The quill's placement, high on the tail's center ridge, suggests a role less focused on defense and more on communication or display. This leads us to the controversy clarity protocol, where we weigh the leading competing hypotheses based on the anatomical evidence.
Communication.
Hypothesis A, visual display, the current scientific consensus. The most compelling explanation and the scientific consensus today is that the tail quills served as a visual signal, possibly for species recognition, dominance, or elaborate courtship rituals. We can use a simple 3D wireframe model created in Blender to simulate how the tail, when raised and moved side to side, would exaggerate the quill's profile. This display mechanic is metabolically cheaper than developing heavy cranial crests or thick armor. Given that the quills are slender and would vibrate minutely as the animal moved, they would have been ideal for maximizing visual impact with minimal energy expenditure. This hypothesis is supported by the fact that many modern reptiles and birds use specialized, non-defensive integumentary structures for display. Hypothesis B. Rudimentary sensory aid, the leading competing hypothesis. A powerful competing hypothesis, which relies on interpreting the Psittacosaurus in its dense vegetated ecological niche, suggests the quills might have been tactile sensors. Could these stiff structures, anchored in the skin, have functioned like rudimentary whiskers or vibrissae, providing feedback about close quarters movement in dense undergrowth? This would be a crucial adaptation for a low-slung herbivore constantly navigating thick vegetation, allowing it to detect subtle changes in its immediate environment without relying solely on sight. The anatomy does not definitively rule this out. sensory organs rarely leave unambiguous fossilized evidence. However, without direct neurological evidence or traces of nerve pathways associated with the quill bases, this remains a purely inferential mechanism, highlighting the intrinsic limits of paleontology when investigating the soft systems of an extinct organism. Ultimately, the analytical deep dive reveals that the bizarre soft anatomy of Psittacosaurus is less of an anomaly and more a stark reminder of the limitations placed upon our science. The existence of these quills forces us to fundamentally adjust our baseline knowledge of this animal, transitioning from the idea of a scaled reptile to a creature possessing complex, unique integumentary structures. We must acknowledge that the specimens we have are products of geological lottery, providing only glimpses into the true anatomical diversity of the Cretaceous world. The fundamental question remaining is which of these specialized roles, visual communication or tactile sensing, provided a strong enough selective pressure to favor the retention and exaggeration of such a delicate, energy-consuming anatomical accessory. The principle of parsimony dictates we must select the mechanism best supported by the available biomechanical and comparative data. As established, the hypothesis of physical defense quickly collapses under the weight of mechanics analysis. The quills are structurally incapable of repelling a predator, forcing our focus entirely toward intraspecific interaction. When we consider the placement and rigidity of the quills, the visual display model gains significant authority. Display structures in paleontology, such as the cranial domes of Pachycephalosaurs or the elaborate crests of Lambeosaurines, are universally interpreted as adaptations to maximize visibility, not as primary defensive armaments. For Psittacosaurus, a creature that lived in visually complex vegetated environments, a highly conspicuous, high-contrast structure would have been invaluable for advertising fitness or signaling reproductive readiness. The tail is a kinetic structure, capable of dynamic movement without the metabolic cost of carrying massive bone mass, as seen in the ceratopsian frill. The quills transform the tail's silhouette, providing an immediate clear signal visible across medium distances. To illustrate this, we examine a 2D vector diagram detailing the caudal musculature. The tail musculature of Psittacosaurus suggests robust yet flexible control, allowing for quick, sharp movements suitable for rapid display. This visual data confirms that the quills would not have inhibited the tail's primary function in balance and rapid locomotion, satisfying the evolutionary cost-to-benefit calculation, high signaling value at a low mechanical cost. This strengthens the scientific consensus supporting the role of the quills as an accessory for visual display, likely linked to territory or mate selection. The leading competing hypothesis, the sensory aid, remains intriguing but suffers from a lack of direct evidence. While it is scientifically plausible that keratinous shafts could function as sensory organs, analogous to the mechanoreceptors found in the skin of modern crocodiles or the whiskers of mammals, proving this requires fossil evidence of fine neurological or circulatory canals at the base of the quills. Such evidence, being soft tissue related, is exponentially more susceptible to taphonomic bias than the quill structure itself, and has yet to be observed. We are left with an unresolvable problem. The fossil record provides the structure, but refuses to yield its functional innervation. Therefore, the synthesis and verdict is clear. The bizarre rigid quills of Psittacosaurus were an essential yet fragile tool for social and reproductive communication. They represent a stunning example of evolutionary convergence, creating a conspicuous social signal through a complex integumentary structure that required highly specific anoxic geological conditions, a taphonomic miracle, to be preserved for us to analyze. These structures underscore a vital truth. For every magnificent bony skeleton we reconstruct, countless intricate details of social signaling, sensory perception, and behavioral complexity have been lost to the pervasive filter of geological time. The Psittacosaurus quills, found in only a fraction of its known population, challenge us to realize that the true anatomical diversity of extinct life is likely far greater than the fossil record currently suggests. The deconstruction of this anatomy reminds us that science is not the acceptance of final answers, but the meticulous, ongoing investigation of incomplete data. What is your hypothesis on the function of the Psittacosaurus quills based on the biomechanical constraints we've analyzed? If you wish to download the 3D analytical model of the caudal vertebrae and the associated quill schematic analyzed today, links to the STL files and research notes are provided below.